Hey, good evening, everyone, and folks here and online. Thanks for joining. We will be we have a set of series of talks lined up, and this is the second storage meetup we are having, and we are proud to host here. And let me go over the agenda today. So the first, the Shiv Moorthy would be talking about Apache Ozone user adoptions. And then I would be inviting Aswin for talking about state of the union of the Ozone project. And then we have Fengnan and Jing Zhao, who would be talking on DataNode local caching for adopting the high density HDDs. And last but one would be on the snapshots in the Ozone. There are a lot of innovations happening there. The Prashant and Swami and Dave would be talking on that. Our last talk would be on Apache Iceberg, one of the exciting talk. And Prashant and Vincent would be talking on that. For the first talk, I would be inviting Shiv Moorthy to talk on user adoptions.
Great, thank you.
Thank you. Welcome.
All right, hello everyone. My name is Shiv Moorthy. I'm the product manager for Ozone storage at Cloudera. And I'd like to give you a short introduction on the motivation for why we built Ozone, and a little bit about the primary use cases that we deal with today. And that'll put everything else in context. Okay, so as a company, we've been running HDFS at very large scale for about 10 years now. So what did we learn from all of this? The key lessons we learned that disaggregation and separation of concerns is very important. Every critical part is a separate service that can be scaled independently. Namespace management, container management, and S3 protocol handling. On-disk representation of metadata that does not require the entire namespace to be in memory. Right? You no longer need to be a JVM tuning expert to run a scalable storage. Efficient block management with support for large or larger block sizes, 5 GB and above, as well as erasure coding for storage efficiency. Efficient recovery in the presence of failures with raft protocols, sub 5 minutes for a large cluster. These are all the things consistently we've been hearing from many of our large HDFS customers. And these are customers who have been running clusters of hundreds of nodes with tens of petabytes around the clock. So we said, okay, let's take these key inputs and design the next generation, right? What comes after HDFS? The primary design goals were to optimize for analytics, fast scans, fast file system operations, scale to billions of objects of various sizes, read after write, strong consistency, right? Modular architecture using industry standard building blocks, preserve and reuse the good parts of HDFS. I mean, after all, HDFS has been around and it's still the de facto standard for performance for some of our largest customers. And ultimately, they would like to make this as simple as possible. Okay, so with that goal in mind, over a year and a half, roughly 2 years worth of effort have gone into this project. And today we're now able to enable brand new use cases, S3 protocol access, auto tiering, which is coming in our roadmap. We also wanted to save our customers money so they could go to denser nodes and much larger clusters. And they would do that by reducing the footprint, and therefore your data center cost savings become more obvious, right? And ultimately, to manage these large clusters, right? Administrative ease of use, HA, better cluster insights via Recon, all of those things were set out as design goals, and we have been able to consistently deliver on those items. So again, this is just a graphical thing of, the motivation behind whether HDFS was enough. Right? What else did we need to do? we are also finding that people want to move workloads to and from the cloud, on-prem to cloud and backwards. They want, which is why we have common APIs, right? That you can use. You write once and run anywhere. Scalability, right? Petabyte scale, thousands of nodes, billions of objects, which is typically orders of magnitude higher than what an HDFS name node could do. Of course, protection, they want to do all of this very safely. So encryption at rest and in motion, highly resilient clusters that are very fault tolerant and completely independent, ideally compute storage separation, right? So we have also managed to cultivate a rather thriving community of open source contributors like yourselves, right? Shopee, G Research, whom we're happy to have here among us, Chihu 360, Preferred Networks, DD. These are all names that are consistently coming up across our community. And we have partnered with Cisco and Intel for reference architectures, which you can also see, right? And so these are the top open source contributors that we have had so far. And just to give you a quick snapshot of who these folks are, G Research is Europe's leading quantitative finance research firm, right? They use machine learning, big data, and some of the most advanced technologies available to predict movements in financial markets. Shopee is, we have some links to the use cases there. They are a retail platform. Preferred Networks, who have had over 2 years of experience with Apache Ozone, have documented their experiences and written about it. And of course, Tencent, which has one of the largest data warehouses and machine learning platforms to date. So all of these, you can click on these links and learn more about. And as of today, we have over 108 petabytes of Ozone data in production. 108 petabytes is spread out across all of our customers that we are aware of, and some folks that are using their, what shall we say, open source version of Ozone. We have 76 different users in the industry, many of whom I have talked to personally, and they come in different verticals: financial services, healthcare, telecom, defense, retail, and others. We've seen phenomenal growth, 54% in just the last quarter of usage, right, of data under management in Ozone. We expect this momentum to continue because of the various benefits of Ozone. Now, in 2023, in our latest release of Cloudera Ozone, these are some of the key features that we have deployed for supporting data volume and growth. Many of these items we will go through individually in the following presentations, so I'm not going to read out all of them, but we'll just call out a few significant ones. Ozone snapshots, Ozone quotas, container balancer, various kinds of recon improvements, all of those things. You'll see all of that in the following slides. Now, before I wrap up, I'd just like to give you 6 key use cases that I am aware of, or how Ozone is being used in the industry today. If you're aware of more of them, I would love to talk to you individually offline to see if there's any other use cases that we can help support. But broadly, S3 API support is a very big and recurring theme among most of our customers, right? Here, the idea is that we have data science and data warehouse practitioners who have many S3 applications that they want to use both on-prem and in the cloud, right? So now it makes administration easier with a single pane of glass, and you can have the same workloads run in any platform. Second use case is consolidating small tenants. Customers who have lots of compute and storage in discrete little nodes everywhere, their use case is to consolidate multiple small clusters on premises, consolidate to dense storage nodes, replace 100 TB nodes with 400 TB storage nodes, and replace an external object store for archival data with a single storage system. And you can have billions of objects on the same cluster. This is the other use case that I consistently hear about. Then I hear about customers wanting to save costs. This is underutilization of either compute or storage. If you are imbalanced in either way, then you can use our data services offering to disaggregate compute and storage, right? So this would help you, bring down data center costs while improving efficiencies overall. Fourth case is, again, this is the S3 standard, but at the same time, people who want to go truly hybrid, which is having workloads on-prem and using our SDX layer. SDX is something that has access policies and data lineage available with it, and that helps you have a consistent experience both on-prem and in the cloud. And there are customers who have told us they have hit HDFS scale limits, either in number of files, typically around 350, 400 million files. If they want to exceed that, then they would need to have Ozone. And there are other scale limits like physical space limits and other things that we need to manage. And finally, the last is the HDFS name node management. Now, because from a business perspective, we designed Ozone to scale linearly and recover much quicker during restarts. And we also have a reduced number of control nodes, which is the SCM and OM nodes, right? And so operationally, you can co-locate this with HDFS. So Ozone clusters currently do not have to be completely by themselves. You can have HDFS and Ozone co-locate and optimize it for various workloads. Okay, so those were the 5 or 6 big topics I wanted to cover and give you an idea of adoption. And I'll hand it over to Shakil. Thank you.
We did it, but it's our adding. What is this? Like to explain it? If there was a way to submit questions from our listeners. We have a method. Possibly Sid.
Yeah, I think the folks can submit the questions on Zoom chat for now. I think we are trying to figure out alternative ways if there is, but right now you can post the questions on the Zoom chat. Feel free to post there.
Yeah. This over. Okay. I can up the up. Yeah. Okay. Can you define so that
Oh, of course, certainly. Sorry. CDP stands for Cloudera Data Platform, and SDX is an acronym that we use for our security layer. Essentially has the Atlas, which is our data lineage offering, Ranger, our access offering, all of that combined. We call that SDX. So essentially Ranger and Atlas combined is an SDX layer.
Thanks, Shiv. Hey, everyone. I'll be giving a talk on the state of the union of Ozone as of right now, and I'll give a quick intro about myself. Myself, Aswin Shakil. I am a software engineer working on the Cloudera storage platform for the past 2 years, and I'm also working on Ozone for the past 2 years as well. So I'm primarily working on Ozone, and I'm also Apache Ozone committer as well. So for the agenda for this talk is that, so I'll be going over the history of Ozone and the current state of Ozone and how Ozone works. So I'll be going over the read and write paths for Ozone and also the new features and improvements that we will be introducing in 1.4.0. This is the newest release that will be coming up next. And also the future roadmap for Ozone. And I can take any Q&As after the meeting. Yeah. Oh, please closer. Okay. So as for the history of Ozone, so Ozone was started. Can you hear me? Do you want it to be closer? Oh, okay. Yeah, I think it should be fine. Yeah, I think it should be fine. Thank you, Ma. So Ozone started as a sub project under Hadoop, and it has all the original creators of Hadoop majorly working on it. You can also check HDFS 7240. It has all the Jiras listed under it when Ozone was started. Ozone was started to address the scalability issues of HDFS. So some of the HDFS limitations are it can support only up to 400 million files and 10 million blocks per data node. But we can go beyond this in HDFS, but it needs a little more engineering effort to go beyond this and break this barrier in HDFS. So that is one thing. And slow startup times in HDFS, if it's a really huge cluster, it may take a few hours to just start up the name node itself. And as for the scaling of block space and block reports, in HDFS, default block size is around 128 MB. And if you consider 10 million blocks, you're getting like 10 million block reports every time from the data node. And it's really hard to scale the block layer and the namespace layer as it is a single component in HDFS. And so in order to avoid all these things, Ozone has a way of separating block space management and namespace management. So I'll be talking about this shortly, and we'll be going over that. And so, Ozone was designed to store billions of objects. So precisely, we can store up to 4 billion of objects, which is 10x of HDFS. And people over in community and here as we are also tested it to be go around like 10 billion objects, so which is around 20x of HDFS. And Ozone was developed as a top level project after 4 alpha release and 1 beta release in October of 2020. And ever since that, I'll just go over Ozone's introduction. So Ozone is a distributed key value store, and it is also an object store for Apache Hadoop. And as I stated earlier, it can go up to 4 billion objects and also up to 10 billion objects. So it has been tested up to 10 billion objects, which is 10 to 20x of HDFS. So Ozone internally uses RocksDB. So conventionally, HDFS keeps all this namespace and metadata in memory, and Ozone moves everything back to a metadata store, which is RocksDB, which is developed by Facebook, and it has been a building block for Ozone from the ground up. It provides a strong consistency and high availability provided by Apache Ratis. So Apache Ratis is just an open source implementation of Raft, and it provides high availability and 3x replication. With Ozone, it also comes with built-in security as with Kerberos, and you can also plug your own authorizers. For example, you can also plug Apache Ranger here, which will act as an authorizer, and it has REST encryption at rest and encryption on wire as well. So Ozone implements Hadoop compatible file system. So basically, it can work out of box with Yarn, MapReduce, Hive, and Spark. So that is one more thing. And as for the Ozone releases, so the first release was 1.0, which was around September of 2020. So that's when Ozone became top level project in Apache. And the latest version is 1.3.0, which was released back in December 2022. And right now, we are in the process of releasing 1.4.0, and it has some really interesting features and improvements in Ozone as well. So the main features that I'll also be going over these features shortly, explaining how these works and a little bit going over it. So we have Snapshot certificate rotation, recon heat map, and OMDB insights and recon. And we also have semantic token encryption, which is one of important boost in OM's performance. And we have HDFS support as well for 1.4.0. So since the release of 1.3.0, we have made around 1,500 commits, and we have changed around 3,000 files and made changes around 240K additions and 50K deletions just between 1.3.0 and 1.4.0. But the count is still going up. The version for 1.4.0 is not finalized yet, so the count is still going up right now. As for the community, right now, Ozone PMC chair is Sammy Chen from the APAC region, and we have 34 PMC members and 70 committers as of today. And committers are from various regions and various countries from US, Hungary, India, China, and Germany. And we also have members actively participating in Ozone from Cloudera, Target, Tencent, Infinster, Oracle, Microsoft, Intel, G Research, Shopee, Qihoo, and Didi. So these people are these companies are actively participating in the development of Ozone, and we have 191 contributors as of right now, and 120 plus active contributors in the last 2 years. And the main branch has around 6,500 commits on the main branch, and 2,430 PRs merged in the past 2 years. So I'll be going over the main architecture of Ozone and the read and write parts of Ozone. But before that, I'll just give some key concepts so that it's easier to understand. So in Ozone, Ozone consists of volume, buckets, and keys. So volume is like the top level entity in Ozone. You can consider volume as like an user account or a tenant. So volume can only be created by admins and deleted by the admins. And a bucket is something which comes under the volume. So there's like a hierarchy level. So volume comes at the top, bucket comes under the volume, and keys comes under the bucket. So there's kind of like a hierarchy in Ozone. So bucket you can imagine as like an S3 bucket. S3 bucket. So bucket can contain all the keys. So keys is just nothing but files here. So as for the Ozone architecture, compared to HDFS, which has where the name node has both the namespace and the block space management, we have separated that into two different components. Where Ozone Manager it manages the namespace management, and Storage Container Manager, also called as SCM, manages the block space management, so that we can scale them individually. And as for block reports, in HDFS, there is a block report for every 128 MB size of blocks. And in Ozone, we have a further level of abstraction called container, which contains blocks. So if you take, by default, the container size is like 5 gigs in Ozone. So if you take HDFS to Ozone comparison, a 5 gig worth of block reports will be like 40 times that of what Ozone offers. So 5 gigs for us is just one report, and in HDFS it's like 40 reports which I have to send to the name node, and we have reduced the container report or block report by 40x in Ozone. So I'll be going over how the general write path goes and the read path goes here. So as for the Ozone write, so whenever there's a client, the client goes to Ozone Manager and says it wants to write a key or creates a create key request, and then Ozone Manager does all the ACL checks for a request for the client, and then it goes to the Storage Container Manager, which is responsible for allocating blocks and creating containers and creating pipelines. So in pipeline is nothing but a group of blocks which is created, group of data nodes which is created based on the storage, based on the pipeline placement policy. So whenever a client says I want to write a file, Ozone Manager goes to SCM and gets some blocks. So SCM, based on availability, if it already has a container open and which fulfills the requirement of the client, it will serve that container to container back to Ozone, or allocate blocks back, allocates the blocks in the container and gives it back to the Ozone Manager, or it will create a new container group, creates a new pipeline, and allocates block from that container and sends it back to the Ozone Manager, and then it gives it back to the client, and the clients write directly to that data nodes. And once the write is success, the key is committed in the Ozone Manager, and once that is done, so the key is stored in Ozone Manager and it's also stored in the data node, your write is done. And this is a general write flow of how write works in Ozone. And as for the read flow, it is also the same kind of logic. So so Ozone Manager is the first point of contact every client goes through. So the Ozone Manager hits, when the client hits the Ozone Manager, asks for the key info. So let's say here in this example, it wants to read the key one. So Ozone Manager has information on what container and what block has the particular information of these keys, and then it goes to SCM and asks what are the data nodes which has these containers. So it will send a list of data nodes which has these containers back to the client, and client can pick from any one of the data, because it's three-way replicated. Based on this example, it's three-way replicated, so it can read from any of one of the data nodes. So that should be enough for read. And one more optimization here which was done here is that so whenever there's a read, we need to hit SCM to get the container information, right? So here in Ozone Manager, we cache the container information. So we know what containers are located in which data nodes. We don't even need to contact SCM to get it. So that is one more hop we avoid, so that we improve the performance of the entire reach as well. So the container location is cached in Ozone Manager. If it's already there, we just get it from Ozone Manager and then read it directly from the data node. As for the new features, so for 1.4.0, we have, as we discussed, we have new features coming up. So I'll be going over some of the features. So the first feature I'll be going over is Snapshots. So Snapshot is being introduced in 1.4.0. So Snapshot is just like a point-in-time view of the file system. So in Ozone, we support Snapshot only on a bucket level. And Snapshot creation is very instantaneous. So we are already using RocksDB to store our metadata. We just need to take a checkpoint of the RocksDB, which is really pretty straightforward, and it's very instantaneous to take a snapshot. Some of the operation which we support in Snapshot is to create, delete a snapshot, and read from a snapshot, and also do a snapdiff between snapshots. And for the use cases, so Snapshot is used for data protection and data backup. So if there's something goes wrong in your active file system, you can still go back to the snapshot and get the data back from the snapshot DB. And it's easier rollback, and for archival, you can just take a snapshot and archive it, or move it to any other, just replicate it and move it to any other cluster for archival purpose. You can do that as well. So time travel between all the snapshots. And as I said earlier, you can do a replication and disaster recovery as well with snapshots. So this is just like a basic, not like a basic demo of how it works. So you just have, so as I said earlier, Ozone Manager, all the metadata is stored under RocksDB. So RocksDB is the metadata management for Ozone. So we don't, unlike HDFS, we don't keep anything in memory. We keep it persisted in RocksDB. So let's consider we have like key 1 and key 2 in our case. So if you do a create snapshot request, what it does is that it just takes a snapshot of the current RocksDB, and it creates a snapshot a DB here. So the snapshot is just read only. So nothing goes or nothing is modified in the snapshot here. Once snapshot is created, you do any key or key write request. So snapshot DB is immutable, so it doesn't happen anything on snapshot DB. So if you do a key write, it will just go to the active DB. So active DB is the actual main RocksDB, where all the operation, key operation, or any operation goes to the actual RocksDB, and snapshot is just a checkpoint. So nothing happens in that side. So if you do a key write, it goes to only the active DB. And if you do another key snapshot request, create snapshot request, it would create another separate RocksDB. And that is also read only. So we can do snapdiff on it. You can list the keys on it, view the keys in it. So you can do everything in it. And yes, and the next feature is certificate rotation. So in Ozone, SCM acts as a root certificate authority. So it creates a trust chain between, first it creates a trust chain between all the SCMs. And then it also establishes the entire trust chain between Ozone Manager, Recon, and DataNodes here. So I'll be also going over what is Recon over the new feature shortly. And yeah, so it establishes a trust chain for the whole Ozone cluster. And after some 5 or some years, the certificate tends to expire, and we had to manually update the certificates. And in the meantime, the cluster might become non-functional. In that case, that is where the new feature comes in. So this basically what it does is that it initiates a new trust chain by renewing all the certificates with the root CA before the actual certificate acquires in the previous trust chain. And the next thing is the Recon. So this is a component, this is a separate component apart from Ozone Manager, SCM, and DataNodes. This is one more component which gives a global view of Ozone, and it aggregates both the data from Ozone Manager and Storage Container Manager, which is a SCM, and gives a pretty good insight on how your cluster is looking at that time. So the one more so what all things it lists is that, so let me just show. So if you go around here, so you can see all the data nodes that are there, all the pipelines it contains, and all the containers and what pipeline it belongs to. You can see all this information, and you can also do a disk usage, which gives what volume contains how many keys, or how much data. So all this information we can get it from Recon. So it's just like aggregation of OMDB and SCMDB. So coming back here, Ozone Recon heat map. It gives a heat map for up to 90 days. By default, it's 24 hours, and you can select up custom. You can have also custom range, which is also up to 90 days. For any 90 days, you can have a custom range, and it would give you a heat map on a volume level, on a bucket level, or on the keys level. So you can also, if you hover over it, it will show how many times it was accessed in this particular custom range, and under any volume or any bucket or any keys. So this is one feature which was introduced in 1.4.0, and the other feature is OMDB inside. So it gives all this information about container mismatch. It's just some containers. So containers are like the building blocks in Ozone. So containers contains the blocks contains the chunks. So containers are only the container information is mentioned. Container information persisted in SCM. So when some container is missing in SCM, but it's found in OM. So OM also has which container has which data. So OM, it is present in OMDB, but it's not SCM. So we can find that information here. Open keys is nothing but the number of ongoing writes that is happening right now at that point. So it would give the insight of the keys which is being written. And pending keys deletion is that the keys that are already deleted in the file system, but it's not yet removed by the background service yet. So that information will also be available here. And the deleted container keys is nothing but it would give the insights of containers which are deleted, but the keys which belongs to that particular containers. And one more is that support for HTTPFS. So HTTPFS provides like an HTTP endpoint for Ozone. Now with that, we can do REST API calls and do all Ozone supported operation through HTTPFS. And it would basically start a HTTP server on Ozone, and all the calls from all the REST calls are converted to file system API calls and then served to Ozone. So for example, one of the use cases is that Hugh uses HTTPFS to read or write through files through Hugh Web UI. So it's just Hugh UI can just contact HTTPFS server, and then it hits back to HTTP. It changes, it converts the REST request to a file system API call, and then serves the request from Ozone. So as for the performance improvement, right now, as I said, I was talking about this earlier. So one of the important change in 1.4.0 is the symmetric block token. So previously, whenever we write or read a block, we issue a block token, so which will be signed by an RSA asymmetric key. But when we are using an asymmetric key, the ops drop to 115K. So in a secure cluster, when you use it, it dropped to 15K. So 15K. When we change this, so the feature proposes to change this. Instead of using an asymmetric key, we use a symmetric key encryption, and the top ops went some 15K to 70K with this. And one of the other improvement is that so to push this beyond 70K, so one of the changes is that to have a OM container cache. So what it does is that instead of going to SCM and get all the container and DataNode details of a particular key or key, when you're accessing a key, it will be cached in the OM side itself. So it doesn't have to go and ask SCM every time whenever you're accessing a key or something like that. So this increased the performance from 70K to 100K ops per second. And there are also furthermore optimization which was done here. So one of the other optimization is to change the Ozone locking strategy. So you can also check I have listed all the JIRAs here, so you can also check those here. Change the Ozone locking strategy and deserialization and key optimization in the right path. So which is also in progress right now. This will also be available in 1.4.0, and a network topology caching, which will be, so it is similar to container caching, but the network topology will be cached on the OM side so that it doesn't do another hop on SCM, and we can increase the ops rate. So with all these changes coming in 1.40, the potential ops could be something around 190K ops per second. Yeah. So as for the future roadmap, Some of the items that we will be working on in the future would be HB support, which will be working shortly, and rolling upgrades. Right now, Ozone only supports Express upgrade. So rolling upgrade is in our list to work on, and storage steering, and also HDFS to Ozone migration path. So this is also something which we will be working on. 2DC stretch cluster deployment, cross DC deployment of cluster, and we have tested Ozone to be scalable up to 10 billion objects. So we want to break that barrier and go beyond 10 billion objects. So that is something which is also on our pipeline, and deduplication and Solar support. This is something which is on our pipeline. Yeah, that is it from me. So for more information, you can always check on Ozone's homepage, Ozone repository. You can also subscribe to the developer channels. We'll be constantly having mailing over there. Thank you. If there's any questions, you can ask. Yeah.
That means
Pure reads. Yeah. So yeah. Right should be. I don't have an exact number on the rights.
this is what it's still got this name on it. Yes.
Yeah. Is there any other questions? Yeah, I'm open for questions.
Yeah.
So yeah, as for the snapshots, I think there is a few questions in snapshot. So there is a snapshot talk after this. So I hope that would be helpful, and the questions will be resolved over for snapshots there. See if there's any other questions.
Question?
All the powers.
Oh.
Thank you. Yeah, my question is, how's the performance about the list operation? I mean, in the public cloud, the S3 list is a kind of expensive operation. So I'm curious about how the Ozone handles the list operation.
I don't have like a particular number on it. So Ozone has different bucket structures. So one of the bucket structure is file system optimized, which is really optimized for atomic renames and deletes. And listing is should be pretty straightforward, but I don't have like an exact number on it.
Yeah, I think we have two notions of storage layouts here, like FSO bucket and whereas the pure object store type of bucket, where pure object store type of bucket will act similar to the S3 kind of behavior, whereas we have FSO type of bucket, which will be optimized for many of these file system type of operations, which will be very fast, as same as regular HDFS file system, similar to that. Yeah, hope that answers.
Thank you.
But es of the Wild. Y no, yo también me quedo sin llegar al gano.
I think someone's sorry. Okay.
If you have any question in the Zoom, but feel free to just post in the chat. It's a little bit hard to hear it. Yeah. Yeah, I think Ashwin will continue to monitor the chart and he will reply if you have any questions. Please feel free to post on the chart. And folks in the room, we have samosas and coffee and all other food here. Please feel free to grab some of your. And Sid is ordering pizzas. Yeah, I think they will come shortly. Yeah. I think our next talk in the line would be by Fengnan and Jing. That's the one, right? They would be talking on DataNode caching techniques to adopt the high density HDDs. So welcome Jing and Fengnan for talking on the session. Thank you.
Cool. Good afternoon, everyone. My name is Fengnan Li. I am from Uber data storage team. I'll be discussing about how we adopting the high density disk in data nodes, leveraging caching and some other mechanisms. So data populates a lot of data intelligence at Uber. From community operations to compliance, as well as different product support like Uber Eats, as well as like Uber Rides, from market pricing, as well as growth. All of these are based on intelligence based on the in-house HDFS clusters. And over years, we scaled our HDFS cluster from a gigantic one in one region to over 12, 15 clusters in one region. And we have 2 regions. We leverage router-based federation to scale out our clusters. There will be clusters for ingestion, for different temperatures of data, and for different usages, even like non-table API usages. So there are a lot of data nodes at Uber, and this is taking a huge cost. We want to leverage or adopting even higher density. We started with 4 terabyte disk, and now in this talk, we're going over into 16 terabyte disk. And the machine is like 16 terabyte with 35 of such disks. It's like 500 terabyte huge machine. And some of the challenges you can see that, first of all, you will experience significant performance issue with very high density of disk, because the overall IOPS is about twice or triple times of the 4 terabyte, but the data volume is even much higher ratio than that. And also with the large data node, the total number of data nodes or the size of a cluster will shrink significantly. And this will trigger other problems like blast radius, or when one data node is down, the process of recovering, replicating blocks to other machines will also be challenging, just because the number of nodes taking the traffic is much smaller. I'll hand over to Jing. He will give over the detailed process of how we adopting the caching mechanism.
Yeah, thank you, Fengnan. So, my name is Jing, and I'm currently an engineer in Uber data platform. And in the meantime, I'm also a PMC member for both Apache Hadoop and Apache Redis, which is the library used by Ozone, right? Okay, so back to this work. So we know overall, the general motivation to adopt this very fat or say high density hard drive SKU for our on-prem HDFS, the very beginning motivation definitely is cost efficiency, right? Because they're cheap, they can store much more data, and the per storage, this kind of unit cost is definitely decreasing dramatically. Actually, it's less than half of the original price. And now actually it's also give us more this kind of benefits while we are doing the cloud migration, because now we are migrating all the data infrastructure to cloud. And definitely we need enough capacity buffer in our on-prem HDFS. So which means we have to be able to fully leverage or utilize all the disk capacity from all these kind of hardwares, right? So there is no way go back. So overall, this gives us a lot of challenges, as Fengnan just mentioned. The I/O bandwidth, I/O, PS, all these kind of stuff is not increasing from these new skills. But in the meanwhile, we store much more data from each of the hosts. So then we need to solve like two issues. One is the I/O performance. The other is about the reliability, just as mentioned by Fengnan. So what can be the potential solutions? So we just did some this kind of a traffic analysis on top of each of the data node. And we definitely have some observation there. So we see like finally the traffic is always focusing on a small amount of this kind of data blocks. So during like a 20 to 24 hours time window, we see like more than 90% of the traffic is only touching around like let's say like is focusing on the top 10,000 blocks. And in our production, usually the average block size is like 200 something megabytes, right? So which means if we build this kind of a cache, right, and just put all these kind of hot blocks inside of the cache, definitely we can offload a lot of I/O from the spinning disks and potentially solve at least the I/O performance issues for us. So we just try to build this kind of cache. And luckily for all these kind of high density hard drive skill, we actually have this kind of 4 terabyte SSD disk per host. So the number is kind of like each host hold more than half petabytes of the data, but to provide a 4 terabyte SSD cache. Then how to leverage this 4 terabyte SSD cache to offload enough traffic so that we can survive the I/O performance or the challenges. This is our target. And as mentioned by, I see a comment just now from the Zoom also mentioned the Alaxio cache, right? So this is just definitely the solution we try to utilize in this effort. So specifically, we just adopt the open source Alaxio to manage this cache on top of the 4 terabyte SSD disk. So the good thing for Alaxio is like it can actually manage the cache at the page level. Each page by default is just 1 megabytes. Remember, like in HDFS, many years ago, like we also have this kind of ping the whole data block right into the memory using mmap and some other commands, right? So that kind of cache capability is always there, but like directly handle the cache at the block level is relatively hard to use, right? And also like bring us a lot of operation cost. But if you do all these kind of cache in an automatic way, leveraging the Alaxio library, and also be able to handle the cache at the page layer with, for example, 1 megabytes, this kind of size, that definitely give us a lot of extra power and flexibility. And talking about 1 megabytes, this kind of size, so actually this perfectly match also our traffic pattern, right? So because almost everything in our data lake is with Parquet format. And if you are familiar with a Parquet reader, it always read a footer, index, etc., then try to read chunk by chunk. And by default, they are reading like kind of like around the 1 megabytes, this kind of size, right? So we even did some further analysis inside of our production cluster. We confirm more than 80% or 90% of this kind of read chunk size is less than 1 megabytes. So which means this kind of page layer cache capability directly coming from the Alaxio perfectly match our read traffic pattern. And we did some extra work, just exclude the non-kind reads, etc., and finally just focus on this kind of read traffic directly from Parquet reader from our on top analytics traffic. RB to him.
I love tools to aid of data. Finding library.
Yeah, so we have two these kind of layers of the trace. Number one, keep in mind in the DataNode, in the code, in HDFS code, there is a trace called a client log or something, right? Client trace log. By default, for read traffic is with the debug layer level, so you don't see those in production. But you can just turn it on, right, on the fly by leveraging those kind of a set daemon log or whatever command, and select, let's say, 10 data nodes, 20 data nodes, turn it on for like whatever time period. Then you do further analysis, right? You can confirm all these kind of read chunk size. Another way is that we also inject some of the log inside of the Presto, right? So which means you collect the further log to confirm the observability, the observations from the data node layer. Then you can also confirm, okay, the read chunk size is similar, this kind of the size range, right? So overall, this gives us enough confidence, say, hey, let's just go with this kind of a setting and with this kind of overall design, yeah. So yeah, then let's move on. So the overall the idea, right? So build a cache and use this kind of actually even before that, one thing I want to mention. So overall idea is simple, just build a local cache inside of each data node. But the question is also like we also have some other option, right? Another option is a kind of like why not build a centralized this kind of a cache service, right? So by side of HDFS cluster, then my traffic always go through this kind of a cache service, then finally back up by the HDFS. So this is, by the way, also supported by Alaxo. They also provide this kind of a cache service capabilities. So the idea is this. So if we want to build another cache service to survive the Uber scale traffic, the challenge will also be on the cache service layer, right? So you have so many read traffic going through all the caching layer, all the worker nodes. And also at that time, I think that their initial architecture also still involved the master node, right? Pretty much just like our HDFS name nodes. Then you have like another headache there, right? Also, you need to maintain the cluster, do all the operations. But if we have this kind of a local cache, the good thing is like you see this kind of a concentration of the traffic pattern inside of each data node. So the traffic pattern is already there. This is a totally cache friendly, right? So which means just directly go with a local, you leverage the traffic pattern which is already shown and observed in each of the data node. You get rid of all the extra burden to managing extra service and also challenges coming from the caching service, surviving the scalability challenges, those kind of headaches, right? So that's why we just go with a local cache. And if you see also similar this kind of patterns, profiles, maybe also think about like how to choose between, they call it cache SDK, which means local library, versus the caching service, right? A remote cache service as a centralized one. Then of course we still need to solve a lot of, not a lot of actually, some like a list of these kind of challenges. So HDFS data node side, this kind of a data block is actually not immutable, right? We have the append. Of course, don't worry too much about the truncate. I don't think a lot of people are using the truncate. So which means like you may have some stale this kind of blocks in your cache if some appending operation is happening, and how to also like decide which version of the block you want to serve to your readers while the appending is already happening. So those are all the things we need to figure out, right? So luckily we have the HDFS generation step, which is the version ID assigned to each of the block to identify different versions if the append is happening. And when the append is happened, then the generation step, that is the version, will be bumped, right? So with this, then we actually can integrate the generation step as the version into the cache to identify different versions of the block cached in the SSD disk, right? Then, which means by finally we can achieve this kind of similar to say like a snapshot isolation as this kind of a consistency model to finally like differentiate like a older version of the cached blocks or like a newer version of the blocks due to the append operation. Then the next one we need to solve is about this kind of rate limiting. So which means you see like the overall we store so much data in each of the hosts. If we just simply allow all the data go through the cache, very possibly we will have a very low this kind of hit rate. And also another thing is we may just write too much data every day into the SSD, right? So we need to solve this kind of write endurance issue for the SSD disk. So that's why we need to build some rate limiting to decide what data blocks, what data can actually be allowed to be kept in the cache, right? So we build this kind of rate limiter, which leverage this kind of access frequency with on top of this kind of sliding window similar to this kind of data structure. And based on that, we can very precisely control, right? So this data is actually like being accessed frequently. We should allow them into the cache. And another direction we are looking into is like whether we can even leverage some higher level traffic heuristics, right? Because you know like what data is hot from the table layer, from the partition layer, from the business use cases. So ongoing plan is kind of like we can also leverage that kind of information, doing certain annotation on top of the data, and finally let the data node understand this kind of information. And also depend on that to even further control what data can be finally cached. So this actually play a very, very important role in our finally in our production, greatly improve the cache hit rate and also guarantee the write endurance. Evaluation and the rollout. So I think anything related to performance is always a challenge in terms of the evaluation, because sometimes you need to identify the key metrics that give you the signal, say, hey, this is good enough to be rolled out into production, right? So what we are doing is like, we of course identify the key metrics to track. Then the next question is like, how finally to do this kind of testing, even with scale, right? So you cannot just launch some limited traffic and see some good performance numbers and be with it. So what we are doing is like we again collect enough traces from our production environment. Then we do certain abstraction, right? So to say like track, for example, the distribution of the traffic, right, on top of the data sets, to track like the offset distribution, to track the read chunk distribution, and finally build them into the abstraction layer to like present this kind of traffic characteristics, right? Then we build extra tools to reproduce the testing traffic, right? Based on the characteristics we abstracted from the production traces. And the tool we are leveraging is just MapReduce jobs like DFS, IO, whatever, as the basic functionality, which means you definitely can launch this kind of a traffic or reproduce this traffic also with scale, right? We actually launched like thousands of these kind of containers doing all these kind of simulated traffic. And in that case, actually, we can evaluate the cache feature with the production traffic profile and also with scale. So this is actually very, very important for overall our evaluation process, as well as like giving us enough confidence before we fully roll out the feature into the production. And also, Alluxio library itself also have some very good features. It provides this kind of shadow mode, which means like you deploy the overall the things into your production, but it will not take effect. It will not really cache your data, but it will track all the metrics. And based on the metrics, you will know, okay, the potential hit rate, right? And based on that, you finally can decide whether I'm doing something wrong or whether everything looks pretty good. And finally, after all these, we build enough confidence and we just roll out this feature into our production. So you can see this kind of a difference, right? So on the left side, you see very high, this kind of a number of the processes actually get blocked by the IO operations, right? On top of this high density, hard drive skills. And after we roll out and enable the cache feature, immediately the number just dropped around 5 on average, usually always below 10 based on our experience. Usually this number means you don't see a lot of, or say you don't see slow read or or whatever slowness in our production. And some other metrics. Overall, we currently see almost 60% of the I/O are offloaded from our spinning disks, and they get landed into this 4 terabyte only SSD disk, which is pretty good. But of course, we still plan to even improve this number. Then on the other side, if we look at the cache layer, the overall read performance, the throughput is definitely much better compared with the spinning disk, right? But of course, this is expected. Yeah, so I think this is the part one, how we leverage the cache to improve or address the I/O performance challenges coming from the high density hard drive skill adoption. Then we still have some other challenges. As mentioned, if we just fully roll out this fat data nodes in our production, right? So due to the increased capacity coming from each of the hosts, then we will have much less of the node. For example, from several thousand to maybe less than 1,000. And on the other side, each of the hosts actually will store much more data, right? 0.5 petabytes. So if you have a data node decom, you have some data node failure, which means you need to do the data recovery. Potentially, you will have this kind of data recovery bandwidth issue, right? So how you can guarantee I lose 10 data nodes and I have enough or similar recovery speed, right, to recover all these kind of nodes. Other if we don't do anything, potentially we may see a much slower and recovery speed coming from much fewer number of data nodes, right? And on the other side, you need to recover much more data due to the increased capacity coming from each of the hosts. So the idea is okay, so we need to since our data node already deployed into the container, then we can definitely do co-location of the data node containers in each of the hosts. And these data nodes actually can come from different clusters, right? And if we mix the data nodes coming from hot cluster with the data nodes coming from the warm cluster, you can even further improve the I/O performance, those kind of issues. So this is what we did finally. So we just cut each of the disk into 2 logical volumes, and then we just place 1 hot data node and 1 warm data node, let them co-located on the same host and even share the same disk. And with this kind of a setup, finally we solved 2 issues at the same time, right? One is the I/O performance, as mentioned. The warm data node definitely will cause much less traffic, but still fully utilize the disk. On the other side, the blast radius, this kind of change can also be further improved, since each of the data node coming from each of the cluster will just use less amount of this capacity from each of the hosts. So this is the final result. So we can see after this kind of co-location, the hot node deployed on that host, they are still generating a lot more traffic. So that's why you see a much higher read throughput. And for the warm node deployed on that host, actually the read throughput is much lower, and which means we actually can just fully utilize the disk and don't just overwhelm the I/O bandwidth. Yeah, so I guess that's pretty much all the thing we want to share. So I think we can maybe Fengnan and I can take questions. Yeah,
I can add up on one thing. So the other reason we didn't choose to have Alexio as a distributed service is it didn't provide enough security support as Uber scale. every data, like all of the clusters in Uber is secure. So that was also part of the reason. I think, yeah, I can take questions and Jing.
There was one question on juice surface. Oh, yes,
I think the TrueFS is kind of like a competitor of Alexio, right? So to be honest, like theoretically for this kind of use case, we a lot of cache system potentially can work, right? Because this is about a local library, but I do think at least we are happy with the Alexio library in our case, and also internally, we in another use case we also shared in Apache Con this year. So Alexio local SSD cache, we also have this kind of collaboration with the Alexio community, right? Leveraging Alexio SDK library to achieve similar goal, but at the Presto layer, right? This is also like the similar work also can be seen directly from the Facebook. They called it Raptor X or something, if I remember correctly. But if you already have some experience working with other, for example, caching library or other offering, I think definitely you can take a try as well, right? So yeah, but overall, Alexio community provide us very good support. Yeah. Yeah, maybe. Yeah.
You talk about the Alexio SDK. Now that, I mean, as far as I know, the Alexio is a kind of service. You still need to deployment the metadata key value, something like that, RockCB. My question is, you choose the local cache. That means on every node that it should have some key values or something like that as a background of the worker. So my question is, what the overhead for each host, and how can you make it high availability?
So you mean the question is more about like from the local cache implementation perspective, how we maintain, or say the Alexio library maintain all the cache storage, or like
not only, but also I'm not sure it's an SDK, but
Alexio perspective, you mean?
Yeah.
Or the cache perspective?
Because it must need KA.
Oh, okay. I see what you mean. Okay. Yeah. Sounds like it should be a question directed to Alexio community. yeah, but I use it. Maybe I can share some of the experience from our Uber side, right? So when we leverage this library to maintain the local, this kind of caching layer, actually, I think they directly talk with the local file system, by the way, right? So they don't directly say like, I also place a RocksDB or whatever. And they also build this kind of a in-memory metadata layer on top to manage all these kind of local pages. So that's their current this kind of implementation. But I guess they are also thinking about some other ways, but they definitely have more complicated architecture if you're talking about like some caching service, right? So yeah, but of course, like you need to finally follow their document to confirm what I talk about here. Yeah. Yes.
I want to drill into the caching performance after you apply the Alexio, because I think we need a lot of work on optimizing the performance, reduce performance, and caching for HDFS and Ozone using different workloads. Most of the time, they just work out okay because OS cache simply just absorb most of the workloads. So you don't usually touch the disk at all. So I was wondering how and what does Alexio do better that is better than the OS cache? Like vanilla OS cache does work pretty well out of box. What does Alexio do better than that?
Yeah, and I think number one is like when buffer cache play a role, we still heavily leverage buffer cache finally, right? So that's always the case. If we look at our current this kind of traffic, I remember like in the past we even see like some repeated traffic, right? Keep hitting the same data set, and finally everything is cached in the memory in the OS buffer cache. And you see the very, very extremely high this kind of a throughput, and finally overwhelm our network, and finally cause an incident. By the way, yeah. But on the other side, if you just look at this kind of normal this kind of traffic pattern, right? We don't have any this kind of a guarantee. Say, hey, the in-memory buffer cache, the size, etc., can just guarantee like everything is going fine with the OS buffer cache can be served from there, right? There are maybe a couple of these kind of reasons. Number one is like these kind of cache, they don't have any this kind of heuristics or knowledge coming from even higher layer, right? So you just blindly based on all these kind of access pattern. But remember, we also have at least in Uber production, we also have a lot of let's say the analytics, this kind of traffic directly coming from, for example, the DataNode decommission, right? The hardware, all this kind of maintenance. We see like usually this kind of traffic occupy almost like 20% of our overall read traffic. This actually will just give you a lot of headaches if you purely just based on all these kind of OS buffer cache, right? To solve the problem. And also the memory size, we just have like a couple hundred gigabytes usually coming from each of the hosts, right? We don't have this kind of a terabytes level, this kind of OS buffer cache to like handle the traffic, right? That's another challenge anyway for us. And in the end, if we look at or find out our solution, number one, at least we have 4 terabytes, this kind of a SS disk, which although is much, much smaller compared with a half a petabyte of this kind of disk capacity, but at least much larger than the memory size, right? On the other side, we definitely can build in a lot of these kind of heuristics, our understanding of the traffic patterns, etc. Right? We build this kind of rate limiter to further confirm, okay, this block is worth to be put into the cache. We also plan to even like based on the data size, data tier, or the business, or this kind of a requirement, and like push down all this kind of knowledge to the local cache layer to further improve this kind of performance. And although this feature is not within our HDFS DataNode local cache, it definitely has already been built into our Presto local SSD cache, which also play a very, very important role as this kind of rate limiter, right? All these things actually give us a lot of extra capability and flexibilities, I think. Yeah.
I would say like the cache was deployed not on all the code paths of DataNode, is mostly on the RAID paths for the right one. That's why Jing mentioned that we have to fix the pen issue. Also, I think Alexio is just easier to configure. It's a software level thing, whereas for kind of like the buffer cache or other memory thing, we have to do a lot of hardware tuning, which is not something software engineers want to do in a short term.
I think I saw.
I think on one slide you had 1,000 petabytes capacity. So is that what you have currently deployed?
Oh.
Yeah, no, in one of your slides in challenges, you had 1,000 plus petabytes. So I was just curious if you actually have that kind of, that's 1 exabyte, right? So do you have? Okay. Okay. And that's on HDFS. And if you're able to share, like, what's your largest cluster in terms of capacity? 300. That's raw capacity. That's the raw capacity. Okay. Okay.
Out. Line.
Okay. Yeah, that's pretty impressive. That's a lot of data.
Just. Oh, that's.
Oh, okay.
Does it work? Okay.
Jing, I have a question. You said like you are using Alexio library, right? So isn't that library is maintaining the heuristics of the data access pattern? So this, in another slide, you said like you are also maintaining the block access patterns.
Actually, the heuristics, etc., is built outside of the library. So we use the library to directly maintain this kind of cache pages, etc., right? And do all these kind of eviction, etc., cleanup, etc. But like we actually have the full control about what data can be allowed to be stored in the cache, to enter the cache. So in the end, they also provide us this kind of a hook interface to make that kind of decision. So very, very easy to do this kind of integration.
Got it. Yeah, thanks. Do you have any blog around that? What kind of changes you made around to the Alexio to feed this kind of data?
We actually, you mean like some document or blog or like whatever, right? So actually, we do have an engineering blog in Uber engineering blog. So you can find, you just use what's the title of that? Yeah. High density, like a hard drive or whatever. You can still find that. Yeah.
Okay. Thank you.
DataNode, maybe DataNode is a keyword. Yeah.
Thank you. Any other questions in the room? Looks like we're good. Thank you, Fengnan.
Hey guys, so we are here to talk about Ozone snapshots. So my name is Prashant, and I will be co-presenting this with Swami and Dave. So this is the agenda of this talk. First, we will talk about what is a snapshot and how does it compare with object versioning that other object stores out there provide. Then we will talk about why do we need a feature like a snapshot, can we live without it, and what kind of use cases it enables. We will also talk a bit about how to use this new feature that we built for Ozone. And then we will go into the internal designs of like how exactly we did it for Apache Ozone. So what is versioning versus a snapshot, right? In object versioning feature that you see out there, you have a single object, and as you make update to that object, you create multiple versions over time. And if you were to compare it with a snapshot-like feature, so what you do here is you take a group of objects and you take them as a unit, and this entire unit moves from one version to another version. And this group always stays in an app consistent state. So here in this picture, you can see that there are three objects, object 1, object 2, and object 3. It's possible that object 1 is modified multiple times and it's, let's say, at V10. Object 2 could be at V20 and object 3 could be at version 30. But together they stay at version 1 of this entire group. And when you modify them multiple times, and let's say you arrive at another app consistent state, that is when you will come to version 2 of this entire group. So the problem that we see with versioning is like there are like over time you end up accumulating too many versions, and then there is a namespace explosion, right? So other object stores out there like AWS3, they provide a feature where you can expire objects over time. But there is a problem with that. What's the problem? What about the referential integrity of object, right? Let's say if you are writing an application where, one object refers to another object and application logic moves to another version of object A, that is V2 in this case, and you have an expiry based on the, aim time of the modification time of the object. So it's possible that, the other object that it refers to, it has become very old and your underlying, object store system expires it. And then you have a dangling reference here. One more problem that you see with the object versioning is here is an example of an application where object 1, it goes through multiple versions. Then you have another object 2, it has its own multiple version, and so on and so forth. And from application logic, if you may link object 2 and object 1, then there is like this explosion of all the different combinations that are there, right? Which version 1 of object 2 with another version of object 1. And then if you add multiple objects and you link them together, you really have an explosion of like all these references. As opposed to that, if you look at the snapshot kind of feature, right? Because you are treating all these related objects as a group, they all together move from one version to another version, and you don't really have this problem. Here's another example of app consistent view. So let's say the application has a very simple logic. It's a financial application. It's taking, let's say $50 from account A and it's depositing it to account B. Now let's say in your object store, you are representing these accounts by 2 different objects. The initial balance amount is 100 for object A, $200 for object B. So there is an intermediate state here, right? Where if you look at the overall amount, if you add it together, it comes out to be $50 less, right? So with the snapshot kind of feature, what you can do is you can take a snapshot at your app consistent state 1. You can ignore all the inconsistent state transition that happen in between, and you can take a snapshot again when the app arrives at another consistent state. So what are the different use cases we enable with this feature? So very basic use case that we have is to have some active object store state. You can take the snapshot and you can keep them around and you can use it for data protection, right? So let's say once you took the snapshot, there are further modifications happening on your object store. And at this point, there is a crash or, because of malware, there is some problem with your data there. You can always recover it from your snapshot. There is another use case, archival and compliance, that it enables. So what you can do is over time, you can take different snapshots and you can keep it in your archival tier and you can restore it as required. Another very important use case that it enables is time travel. But this is not a single table time travel. So in your object store, you can have in your bucket, you can have multiple tables, right? Or you can have your entire database. You can treat all of that as a unit, and you can do a time travel for this entire unit. Again, very similar kind of use case. Over time, you take different snapshots. Again, all app consistent states at different times, and then you have a snapshot repository. Using this, you can restore application state to any specific time. And another very important use case that it enables is your full replication to another remote site for DR purpose. So again, you have the active object store. What you do is you take a snapshot, you have a replication engine. After you take the snapshot, you let the modifications happen on your active object store. You take this snapshot, it provides a stable image while you are replicating it to a remote site. And as part of replication, it also enables delta replication. So for delta replication, this feature provides another sub feature. We call it the snapdiff. So what you can do is you can take the snapshot, some initial state, let some changes happen in your active object store. It arrives at V2. You take another snapshot at time T2. And then what you do is we provide a primitive called snapdiff. You give it 2 snapshots, and it can efficiently calculate what is the delta between those 2 snapshots. You can only replicate the incremental changes that happen. You can apply that incremental delta on the remote site, and you arrive at the next state. Now that we have seen like all the different use cases it enables, let's look at how I can use it, right? So if you look at Ozone, your Ozone namespace, it has different volumes. You can think of it as different bucket namespaces within your volume. Inside volume, you can create multiple buckets, and within buckets, you can create multiple keys. So this like multiple keys that you create within a bucket, that we can think of it as your active object store namespace, where the changes are happening in your bucket. And we provide this snapshot feature initially at bucket level. So what I can do is I can take the snapshot snap on this specific bucket V and Bn. It will capture whatever number of keys were there in the bucket at that point in time. And all this state is available through this hidden namespace .snapshot. And if you look at the full path, how I can access it, it's just like how I would have accessed the same key in active object store, like /v2 bn k4. I'm just going to this hidden namespace here, /v and /bn under the bucket, .snapshot, the snapshot ID, and then the key name. And this way I can access multiple snapshots here. Another important thing about snapshot is they are space efficient. So they share the common space that is not modified between multiple snapshots as well as the active object store. So in this picture, let's say your active object store is at this initial state. There are no snapshot. And in the active object store, the logical amount of space you are using is 100 gig. The actual physical space is also 100 gig. Now you take a snapshot in this state, right? So if you look at the active object store, the logical space that you have is about 100 gig. You have another 100 gig of logical space in snapshot 1. But since all the space that is common between the snapshot and the active object store, it's shared. If you look at the actual physical space, it's only 100 gig. If you delete 10 gig of data from active object store in this case, so if you look at the logical usage, it's 90 gig in the active object store. It would still be 100 gig in your snapshot. And if you look at the actual physical space occupied on your drives, it will still be 100 gig. The reason being the original 100 gig is locked in the snapshot. Even though you have deleted it from the active object store, that 10 gig is still available in a snapshot. And in this state, if you add another 20 gig of data in your active object store, if you look at the actual physical space, it will move to 120 gig. 100 gig originally logged in the snapshot, plus the 20 gig of new data that came in the active object store. So the feature that we have implemented for Ozone, it's very space efficient. It shares all the common data between different snapshots as well as the active object store. So in terms of APIs, we provide the snapshot create and delete APIs. Our snapshot create API is instantaneous. regardless of the size of your active object store. You can have a 10 petabyte object store. When you issue a snapshot create operation on that, it's instantaneous. It almost returns immediately, sub-second. Internally, Ozone maintains the create order of different snapshot on an individual bucket basis, as well as the global order. The reason I'm mentioning it is because this order is important when we delete the snapshots. So snapshot deletion is also an instantaneous operation. Space reclamation for the deleted snapshot, it's done in the background. And we don't put any restriction in the order in which we will allow deletion of the snapshots. It's different from some systems out there. Another useful API that we provide on top of snapshots is snapdiff operation. So given any two different snapshots of the same bucket, it can very efficiently calculate what is the delta change between these two snapshots. And the amount of time it takes to calculate the diff is proportionate to the amount of change. So it's possible that you have, 20 petabyte object store bucket. But if the incremental amount of change that is only like 10 gig between the two snapshots of this bucket, the time it will take for computing the snapdiff will be proportionate to this only incremental change that we did. So this is what the output for a snapdiff operation looks like. It will precisely tell you what keys were added, deleted, modified, and renamed. It's an asynchronous API, and you get the paginated response. Now, how does it all work? So if you take a quick look at Ozone architecture, we have a namespace management layer, Ozone manager. We have block management layer. We call it storage container manager. And then we have the individual data nodes, right? And then we have a bunch of other components, Ozone Recon, and then the Ozone console, where you can see what's happening in the cluster. And clients can connect to the cluster they can talk to Ozone Manager for any metadata operation, or for doing any direct IO, they can directly talk to the data nodes, right? So now let's take a closer look at Ozone architecture for how we implemented a snapshot here. So if you look at the Ozone Manager, it maintains a map for every object. It maintains a map of what are all the different locations where I can find its data, right? So if you look at this key one, it can say that key one, its data I can find in container 1, C1, and block 1. That's like how we refer to different blocks in Ozone. There is a container ID and block ID. Container ID, you can think of, the concept of container, you can think of it as a super block, right? In HDFS, you used to have like 128 MB block size. But in Ozone, we always, we think of block references as the container ID, that is the super block, which is about 5 gig in size, and the individual blocks inside that container. So if I look at this reference, right, I know that the C1B1, right? The mapping will tell me that container, this particular container C1, I can find it on data node 1, 5, and 6, right? So then these are the 3 replicas of this container. Then I go to these 3 different data nodes, and here within the container, I can find this block B1. So that is how I find out where I can locate the data for this particular key. Now, in Ozone architecture, whatever we keep on the data node container, it is pretty much immutable. Once a block is written, it cannot be modified. So now, how do we make use of all this information to create snapshots for Ozone? Whatever we have in the data node is immutable. Whatever information we have in the storage container manager, it can be rebuilt over time based on the container report that SCM receives from different data nodes. And then if you look at the Ozone manager, which is maintaining all the metadata for Ozone, that is our key piece of information. If we can just snapshot this, that is enough for us to create the snapshot image of everything inside your Ozone namespace. And we will make use of this. Well, not quite there yet. So we also have to make sure that we have this block deletion service. So any blocks on the data node that are not referenced by your namespace, it just reclaims it. So now we have to make changes to it to make sure that it's not just the active object is stored namespace. We also have to make sure that the blocks are not referenced by your snapshots. So now that we know that we have to take a snapshot of Ozone Manager, let's look a little bit more into what do we have inside the Ozone Manager. So Ozone Manager typically runs in a HA ring. We have 3 different nodes that are running Ozone Manager code. Whenever write operations come to Ozone Manager, it first gets written to a raft log, and we run a raft ring between these 3 different Ozone Manager nodes. And at some later point of time, this raft log is replayed on the underlying LSM database. So in our case, that's RocksDB. And again, we will make use of this information. So what happens when we take a snapshot, right? So let's look at the raft log. So all the different operations that are happening in Ozone Manager, all that is going in raft log. In this particular example, you can see that all these operations we have divided into 3 different groups, right? So there is a bunch of operations that happen, then there is a create a snapshot operation that happened, and then again bunch of some more operations, right? So internally RocksDB, right? It maintains all of this information is in SSD files. So SSD files are immutable. Once they are written, they cannot be modified. At some later point of time, they can be compacted. That we can deal with separately. But for all practical purpose, they are immutable. So first commit batch, we replay it in the RocksDB, and we arrive at these 3 different SSD files. When we come across a create a snapshot operation, what we do is we create a checkpoint on that. So based on the snapshot ID, we create another separate directory. We link all these, hard link all these existing SSD files. And that's it. You have your snapshot available in this new directory. And the subsequent transaction, they can continue to, you can continue to replay them on your active object store RocksDB directory. So this is pretty much in a nutshell how a snapshot operates. There are like bunch of complexities that probably, in some other session we can deep dive into, but this is pretty much an overview. So to talk about some more details about the snapshot, I have Swami here with me. He can go for that. Thank you.
Hi, everybody. So now that Prashant has covered snapshots, how snapshots have been implemented in Ozone on a high level, let me just deep dive into how snapshots have been specifically implemented in Ozone. So Ozone snapshots basically leverage RocksDB checkpoint mechanism, which does nothing but it flushes the wall and creates a checkpoint. Given a directory, it just creates a checkpoint for the RocksDB. And taking a checkpoint of a RocksDB is very instantaneous. It doesn't copy any data, as Prashant mentioned. Just as long as the checkpointing directory is in the same file system, it's a mere hard link, and no need for copying the data. And we use Ratis to maintain the consistency to maintain a consistent view of the whole RocksDB state across all the OMs for HA purposes. This image basically gives the internal details about how Snapshot has been designed and how we have plugged in the Snapshot functionality into our existing Ozone manager. So if a client wants to come and take a snapshot of the existing system, so if you follow the blue line, we have the Ozone metadata manager. So the client goes to the active object store, and we take a checkpoint of the active RocksDB instance, and we actually have a shared RocksDB instance, which is nothing but a bunch of RocksDB instances. So and that's we take a checkpoint of the existing active RocksDB instance. And if based on if you follow the green path in the image, based on any reads, so the reads are basically redirected to the active object store and the snapshotted RocksDB instance, respectively, based on the path we are trying to read. As in, if we are trying to read a key from the active object store, we will read that particular key from the active RocksDB instance. And if the key belongs to a snapshotted RocksDB instance, we would be reading it from a snapshotted RocksDB instance. And if you see, we have the snapshot aware key deleting service, so which is basically responsible for reclaiming all the underlying data blocks corresponding to a particular key that has no reference in any of the snapshots. So why is this important? Because if a client deletes a particular key, we cannot directly delete that particular key, because that key could be referenced in one of the previously created snapshots. So that is where this whole service comes into play. So we will be going a bit into detail in the upcoming slide as to how space reclamation exactly works. So let us take a scenario where to see how space reclamation works in a typical Ozone Ozone bucket where the snapshots are not involved. So this is how a typical Ozone metadata, Ozone Manager metadata is laid out. We have a key table, we have a deleted table, and we have a bucket table. So if a delete key request comes from a client, so what we do is we simply remove the key table, the key 5 from the key table, key 5 entry from the key table, and we actually move that entry into the deleted table. And now we have a background key deleting service, which basically picks up all the entries from the deleted table, and is responsible for deleting the underlying blocks. What it does is just sends a request to the storage container manager to delete the blocks, which in turn sends a request to the data nodes to delete the underlying blocks. So now let us jump on to how space reclamation exactly works when snapshots come into play. So consider this is a bucket 1, and we have key 1 and key 2 in the key table in that particular snapshot file. And this is how the active object store looks. So we have 2 entries in the deleted table, that is key 2 and key 4. So can we really clear up, can we really delete both of these keys? Can we reclaim both of these key 2 and key 4? Not exactly, right? Because we have, for the key 2, we have a reference in the previous snapshot, that in one of the snapshots in snap file. And we can, though we can obviously reclaim the key 4, right? So that is how space reclamation in a snapshotted environment really looks like. So we check on to the previous snapshot in the snapshot chain, and we end up reclaiming the keys, which can be really reclaimed. So now let us jump on to how we do the out of order snapshot deletion, as in deleting any snapshot in a given snapshot chain. So in Ozone, we typically maintain all of the snapshots as a snapshot chain. So consider the case we have snapshot 1, snapshot 2, and snapshot 3, and this is how the key table and the deleted table entry typically looks like. So if a client wants to really delete the snapshot 2, so we cannot really drop the RocksDB instance, and we won't be good, right? So we would have to we can potentially reclaim a bunch of keys, and also we need to ensure that the keys that have been deleted in the snapshot 2 are ensured in the correctness. So in this scenario, we have like key 4, key 5, and key 6 that have been deleted. Key 4 and key 5 cannot be really reclaimed because there's a reference to it in the snapshot 1, and we can't really reclaim the key 6, which is reclaimable because we don't have any reference to that particular key in the previous snapshot. So we end up reclaiming the key 6. But what do we do with the key 4 and key 5? So all we do is we drop the RocksDB instance, and we get those key 4 and key 5 entries in the snapshot 2, a deleted table, and we merge the deleted table entries with the next snapshot. So our snapshot chain after the snapshot gets deleted becomes snapshot 1 and snapshot 3. So this is how we handle snapshot deletions. So here we have key 4 and key 5 in the deleted table. So now let us jump on to another feature that is supported. It's the snapshot diff. So snapshot diff typically leverages the LSM, is meant for LSM architecture-based databases. So where all of the new updates are typically written to new SST files, new immutable SST files, which basically stands for static sorted table files. So let us look at how typically a write is handled in a typical LSM-based database. So we have a write request coming in, and we have an in-memory mem table, active mem table, and we have a background immutable mem table which is present, and we have the persistent wall. So when a write request comes in, the active mem table is actively modified, and also the same thing is also written to the persistent log for crash recovery purposes. And as and when write requests come in, like the mem table might get full, and the LSM tree basically switches the in-memory mem table, and the immutable mem table is then flushed into the SST file, into an SST file, and here we have a SST file 3. So this process keeps on happening, and we create multiple SST files. So this is what a typical RocksDB SST file content typically looks like. In this case, key 1 is nothing but the key that got created, and the sequence ID is nothing but the internal transaction ID of a RocksDB, where that's the transaction number at which the key 1 got created, and the type is nothing but the type of entry in that SST file. So type 0 basically stands for the tombstone entry, and which basically means that when a typical delete request comes in, we have a type 0 tombstone entry. And so in this case, for key 4, we have created a value 4, which basically stands with the type 1. So now how do we really perform the snap diff? Reading through all the SST files wouldn't be really optimal, right? So consider this case where when the moment we took a snapshot 1 and we had these list of SST files, that's SST file 1 and 2, and we made a bunch of updates, and we created SST file 3 and 4, and then we took a snapshot 2. So if we take a snapshot diff, but perform a diff operation between snapshot 1 and snapshot 2, ideally just getting the contents of the SST file 3 and 4 should be sufficient, right? Which basically has all the updates. So what exactly would happen in the case of compaction? So RocksDB provides us with listeners where we can actually track all of these compactions in where we actually track all of these compactions in a DAG. So let us go through a typical timeline of what happens when we create consecutive snapshots for a particular bucket. So yeah, take an example. So this is the active object store, which contains SSD file 9, 11, 13, and 15 respectively.
Here you go.
So let's continue. So where were we? Yeah. So we took a snapshot of the active object store, and this called snapshot 1 with the following SSD files. And a bunch of write operations actually happened, or update operations happened over time. And this is how the active object store currently looks like. So that's 17, 19, 21, 22, 24. So what really happened to the previous SSD files is that it basically got compacted into the other SSD files, and 22 and let 22 and 24 be the new updates. And we took another snapshot 2 again. Sure. So the process would keep on happening, and we have the object store. This is how the view of the object store looks like. So we have the 27, 28, and 29 SSD file, and 24 SSD file 24 remaining the same, and we have a new SSD file that 32, which has the new update. So now let us look at how we are actually using this DAG and what our compaction DAG really contains. So in this case, the diagram basically explains how the SSD files have been compacted from one state to another. That is SSD file 15, 13, 11 have been compacted to form 18, 16, and 17 respectively. Oh, sorry, I missed SSD file number 9 as well. There are 4 SSD files which got compacted into 3 SSD files. So this is the state where we took the snapshot 1. And this is the RocksDB state when we took the snapshot number 2. So what exactly would be the SSD files which contain the new updates? It would be the SSD files that have been marked here, right? So basically the files which have no which are not present in these SSD in the snapshot 1's SSD file list. So that is basically the 26, 24, 22, 20, 39, 37. Sorry, I'm just reading it out. So these are the Delta SSD files which we have to read to figure out the snapshot diffs. So let me just go through how the snapshot diff flow really goes through. So here we have the client, and who has requested us a diff between 2 snapshots for the same bucket, that's snap1 and snap2. So we have a stored snapshot diff. We if at all there's a duplication in the request, we actually if the snapshot has been pre-computed before, the results have been pre-computed before, we just serve the request then and there. If not, we go further. We have to compute the whole diff again. So we have the in-memory compaction DAG, which will give us the list of SSD files that are different between the 2 snapshots. And now we discard all the SSD files that don't belong to that particular bucket. And now and then we get the key set that by reading each of these individual SSD files, we get the keys of the keys that have been modified in the whole since the creation of snapshot 1 and till the creation of snapshot the target snapshot. And then what we do is we simply just read these keys from their respective RocksDB. That's the source snapshot and the target snapshot. And then we actually store these diffs store these diff and actually like generate the snap diff and serve the request. I hope that is clear. So there's a small demo we recorded, which actually explain all the operations we are currently supporting. That is creating a snapshot, listing a snapshot, reading from a snapshot, and reading from a snapshot after updates, after the same keys have been updated, and the snapdiff operation. So here we have So here we are actually creating 5 keys in an existing Ozone file system, and we created a volume. We created a bucket, object store bucket, and then we put all of those 5 keys into that particular bucket, and then we created a snap one over that bucket. And now if we do an ls on that particular ls, list all the snapshots corresponding that put to that particular bucket, we have a snap one that got created. And now if we do an ls into that particular bucket's snapshot snap one, we'll have all the 5 keys that got created. Now, let us say that we actually are deleting the key 1 from the existing bucket, and also the key 2, and we are renaming key 3 to key 3 renamed. And we are also adding, we are actually updating the key 4. Oh, sorry, we are creating a key 11 in this case, my bad. So after that, if we do a list, these are all the keys that are in the active object store. Now, then if we do an ls again, we see that the contents of the snapshotted bucket is still the same. That's key 1, key 2, key 3, key 4, and key 5. And now if we create a snapshot 2 of the existing active object store, and then we list all the keys, we have the corresponding keys that were there in the active object store. And if we do a diff between the 2 snapshots that got created, so this is the output we get. Like we deleted key 1 and key 2, we renamed key 3 to key 3 rename, and we added another key called key 11. So yeah, so this is all I have. Now let us jump on to the kind. Yeah, so let us jump on to the kind of snapshot scale, the scale testing we have done on Ozone snapshots. Dave is going to take over from here.
Hello, I'm Dave. So I'll briefly talk about the scale testing for Ozone Snapshot. So basically, we test 3 perspectives, creating a massive amount of snapshot, at least keys in those snapshots, and do snapshot diff between those snapshots. And currently, keeping the Ozone cluster up and running, we can successfully have a 25K snapshot in a single Ozone cluster, but more aggressive scale testing is coming. We will share the result once we get those part data. So you can see, okay. So there's an important part we want to make sure, because snapshot is all about store metadata of Ozone keys, and those data are stored in the RocksDB, and all the mem table in RocksDB are actually using the off-heap memory. So we want to make sure the off-heap memory is under control when we create massive amounts of snapshot. So this is part of the test data, you can see we monitor when we create snapshot from 1K to 13K, the off-heap memory increased from somewhere 300 megabytes to maybe 3.5 gigabytes. So actually for this cluster, I think it's roughly somewhere between 2-3 million keys. Yeah, it's not very big. So yeah, so basically we want to make sure the off-heap memory is under control when we create massive amount snapshot. And what tool we using to monitoring off-heap memory? We use JMalloc. So it basically create a heap off-heap memory dump for every specific memory allocation happening in your machine. You can configure that. I usually configure like 1.5 gigabyte memory allocation for every 1.5 memory allocation changes in the Ozone, and the JMalloc will dump a heap profile. So this is an example like from one of the heap dump. So you can see how many bytes used by which part of functions in RuxDB. Okay, so I guess that's it for my part.
Yeah, we can take questions if any. No questions, that's good.
Any questions in the Zoom, you can post on the chat.
Yep.
Basically, nationals.
On the layer, underneath, directly from the Ozone, then we have this kind of Ozone native snapshot. Then up layer, maybe Iceberg, we also have those kind of a snapshot. Any plan to even have some alignment or even further integration between these two different layers of those kind of snapshots? Right.
Yes.
Always a question when people also customers ask, right, which layer of the snapshot should I use? Something like that. Yeah.
Yeah. So what you have in Iceberg is a single table level snapshot. But what Ozone provides you is on an Ozone bucket, if you have multiple tables, or you can have the entire database, right? So you get a snapshot of the entire thing. You get the multi-table snapshot. So it again depends on your use case, what you want to achieve. If your application is such that it moves from one consistent state to another by making transformation to multiple tables, then Iceberg snapshot is not going to be enough for you. Then you will have to rely on something like Ozone for the underlying storage. Okay. That answers your question? Yeah. Okay. Any other question? No. Good. Thanks. Thanks, everyone. We have one more.
Yes, yeah.
We are taking a couple of minutes break here. Yeah.
Hello, good evening, everyone. My name is Kulandaisamy. I'm the data warehouse architect and also Iceberg architect at Cloudera. I oversee data warehouse compute engines in Cloudera and also Iceberg innovation and roadmap within Cloudera data platform. All right, in the first talk, Shiv was presenting Iceberg customer use cases, the deployment model. Second talk, folks from Uber talked about their scalability and performance challenges. In the third talk, we did deep dive into Ozone, some of the internal details of that. In this talk, what we're going to cover is how do we basically combine the best of the breed two technologies, Apache Iceberg and Apache Ozone. And combining these two technologies, how you can basically take your scalability and performance to the next level. So in the first part, I will talk about Apache Iceberg, what it brings to the table, how it is helping our customers to scale to petabyte or multi-petabyte scale and provides performance and scalability, and bringing a lot more differentiating capabilities compared to other open table format out in the industry. And my colleague Prashant will then talk about how do we integrate Apache Ozone with the Apache Iceberg and some of the best practices we will cover and wrap up the talk. All right, so as everybody here knows, the key challenges in the industry today, as the explosion of data happens, you are faced with speed, scalability, and also evolution of data. Whether evolution of data means you are adding more partitions to the data, or your schema would be changing constantly because to dealing with that. On top of all of these, you also have consistency, correctness, and ACID capability. So in the big data world for the last 2 decades or 3 decades, people basically compromised on correctness and consistency, and they went with scalability and ease of use. But then you naturally can't live without correctness and consistency. You can't make decisions and business insights with the eventual consistency model of data. So how do we solve all these problems? On top of these 3 challenges that are already existing in the industry, there's one other challenge, which basically every enterprise out there today, they don't use one platform, one software stack. Each enterprise, big Fortune 500 companies or even smaller ones, they use different software stack. Each of the line of businesses in the deployment, they can have their own compute engine. They can produce their own proprietary data format, and for various reasons. But then what they really end up with is they don't have a unified, single curated data lake. Even though that's the ideal state they want to end up with, what they end up really with is they end up with a data puddle. And each line of business have their own data that they cannot be consumed by the other line of businesses, other departments or groups within the company, because each of the compute engine is writing in its own proprietary format. So that's the challenge that basically leads to this picture here. And this is a typical architecture in the deployment that has been there for the last 3-4 decades. Your OLTP system or point of sale systems will feed in all the transactions, and you'd be scaling well to probably 1 million transactions per second. You have a really awesome cluster that is doing a lightweight transactions, feeding into that. And from the point of sale or OLTP systems, then you take that, feed it into your historical data through ETL for your BI and analytics. Then your data really grows large. You can't scale, and they want to do a segmented analysis. For marketing department, they want to create an ETL. For customer insights, sentiments analysis, they want to create a separate ETL. And you end up with this complex ETL pipelines. And this is just one particular line of business. If you think about like a big enterprise company may have 10 line of businesses, and this actually proliferates. And add on top of this, each line of businesses may have their own proprietary software stacks. So they constantly end up with the replication, copying data from one place to the other. So this challenge has been there for almost 3 decades, and customers are now, the cost is quite prohibitive. It costs a lot of time to maintain and manage it, and skill and talented people to run this whole operation. So they have been looking at how do we come up with a unified data lake. And that is where Iceberg comes into picture. With the open table format, where it is supported by a wide array of compute engine, you have single copy of data that any compute engine supporting Iceberg table format can read and write. Now it eliminates all this complex architecture of constant ETL pipelines, data duplication, replication, and the scalability and performance challenges. So let's talk about Iceberg. So the history of Iceberg is basically, it was started in Netflix, and one of the founder, Ryan Blue, was also an ex-Clouderan. He was ex-Clouderan, and he went to Netflix. At Netflix, they saw a sheer volume of data challenge. So they had about 120 plus petabytes of data that they need to really handle, query, scale, and perform. And how do they handle? They basically went through the same challenges of deploying HDFS clusters and Hive tables. And they quickly learned that this is not going to scale. Not only it was not scaling, it was not providing the consistency, correctness issues. So they actually started this project and then eventually contributed it to Apache Open Community back in 2018. Now, let's talk about what the challenges are with Apache Iceberg, right? Let's just compare and contrast from a Hive external table, which everybody knows about how it works, and how does it compare and contrast with the Iceberg table. In the Hive external table case, the table is basically made up of directories and set of files in the directory. And the partitioning that was supported was basically encoded in the directory naming conventions. So we will have to look at the directory naming and say, okay, this directory is, if this table is partitioned by month, then you would have the naming convention will be encoded to say, this is partition for January, partition for February, and so on and so forth. But it did not provide the correctness and consistency or atomicity. Anybody can drop in a file into a directory and hope that this will be read by somebody. And so you'll have this phantom rows appearing and disappearing dynamically on the fly. And there was no guarantee of correctness. There is no guarantee of consistency. On top of that, it didn't provide any of the schema evolution, like you can't dynamically add columns, remove columns. You can't dynamically evolve partitions on this Hive external tables. If you have to change because your volume of the data is really growing exponentially and you can't scale it, you want to go from, for example, a table that is partitioned by year, you want to repartition it to a quarter or monthly partitions. You have to redo everything, regenerate the whole thing to a newer partitioning scheme. All of those challenges people were dealing with. Now, with that, you can see that on the right-hand side, Iceberg basically solved all of this problem by simplifying this whole metadata architecture and file systems. The top-level metadata basically points to the current snapshot of a table. And it is all operating on an immutable model. Any change to the table creates a new snapshot. And the top-level snapshot will then point to a secondary tier of metadata that points to the manifest list and the list of manifest files. And the leaf nodes are actually the data files that are pointed. So every change that need to go through a catalog or a meta store that provides this atomic operation of swapping the top-level pointer. And that is how you guarantee that every change is consistent, committed, and providing your atomic capability. Right, so let's look at the structure of the Iceberg table itself. Oops. A little bit deep dive on this. So the top-level metadata, which is maintained by your catalog. By the way, Apache Iceberg supports wide array of catalogs. In Cloudera data platform, we have standardized on HMS as our meta store. The top-level hierarchy in the meta store provides your snapshots. So it tracks all the snapshots, and that's how you can also do time travel. The second tier basically tracks all the partitioning stats like min and max, lower bound and upper bound for partitioning, lower bound, upper bound for columns. So you can quickly do a file pruning, partitioning pruning for your query processing. And the bottom layer, as I mentioned, basically Apache Iceberg supports three open file formats, Parquet, Avro, and ORC. All right, at Iceberg and Cloudera, we have actually made Iceberg as our strategic direction and our foundation layer for our open data lake. And Cloudera is basically managing 1 zettabyte of data combined. And we are standardized on Iceberg. And in 3 to 5 years, we're basically making sure all our default table format, all our data that we manage will be on Iceberg. With that, how does Cloudera Open Data Lakehouse fit here? So as I mentioned, Iceberg is our foundation for our data layer. And all our compute engine, all the way from ingest to AI, edge to AI, has been all integrated fully with Iceberg. You can take our NiFi's Flink compute engines to stream data in, and that can be consumed. The same single copy of the data can be consumed by our data warehouse engines like Hive and Impala, our data engineering engines like CDE Spark, and CML for machine learning and modeling. Let's very quickly high level the capabilities. I'm going to only touch on the key differentiators. I'm not going to go into drill down each of these. The key differentiators are obviously ACID transaction. This is one that Iceberg set out to solve so that you can guarantee correctness of the results, consistency of the data, and also scale and perform well. Time travel and table rollback. As I mentioned, the top layer, it is tracking every change is immutable and creates a new snapshot. Because it's tracking all the snapshots as the table evolves through the changes, you are able to go back and do time travel either by timestamp or using a snapshot ID. It also helps if by mistake there was an error, you deleted a bunch of records, you can actually go back and roll back your table to the previous snapshot and recover from it. In place table evolution, which supports both schema evolution as well as partition evolution. And partition evolution in particular is really smart enough to say you don't have to have a column specifically in your schema to leverage your partitioning during query processing. Iceberg also supports much more advanced capability in a sense that you can use a base column and use a transformation function to transform the base column to create a partitioning. An example would be you can store a timestamp column, but your partitioning key could be day or month or quarter. And you take the timestamp column and transform that into a quarter and create a quarterly partitions. And the neat thing here about is that it remembers how the transformation happened or transformation function in its metadata. And so users don't need to really know about how the physical layout of the table is, how it is partitioned. Because in the olden days, before this partition evolution, you need to have explicit column in the schema. And then your query need to have that column in your predicates in order to leverage the partitioning. Without that, your query processing will not be able to use the partitioning, even though your data is partitioned. So here, because Iceberg remembers this transformation in its metadata, you don't have to change your schema. You don't have to change your application. So significantly improving your productivity. So think about you have an application of hundreds of Spark jobs. You don't have to go and change every Spark SQL to say, I need to change from my quarterly predicate to a monthly predicate because I changed my partitions. It's also on-the-fly dynamic evolution. What it means that you can change your partitioning without requiring any data movement. It will basically start laying down the new data based on the new partitioning scheme while remaining the old data in the old scheme. And hides all this data processing from the end user. When you're doing a query, you basically knows that your older data are in quarterly partition. If you transform that into a monthly partition as a new data, the query processing knows about that and it will do a split planning and query the data and produce the correct results for the application. So that significantly removes all the burden from the end users, from the application developers, and the admins. In Cloudera Data Platform, we are the first one to support and deliver replication for Iceberg tables. And this came out in our private cloud-based 7.19 release that we GA'd last month. And no one in the industry has actually supported Iceberg replication, and we are the first one to do that. And this actually helps us to do HA, disaster recovery, or other user requirements that they have. All right, so we talked about in the first slide, the big data challenges. I showed a big picture of your ETL, OLTP data coming into ETL, into a big warehouse, and going into multiple ETL chains through a data mart solution. How does Iceberg solve this? Because it is an open table format, you can have a single curated data lake. And data lake is now become a reality as opposed to a concept that people used to be. And they all have this data puddles without having a real data lake. And so now we can create a real data lake that can be shared and accessed by array of compute engines on a single copy of data. All right, so with that, I'll hand it over to my colleague, Prashant, who will go over Apache Ozone. Thank you.
Thank you, Vincent. Yeah, so today we have been talking about Ozone. So this is just, some background on Ozone. It was created to address the scalability issues of HDFS. It's designed to handle like billions of objects. We have tested it up to 10 billion objects. And then, and that limitation is also coming from the underlying RocksDB. It's still scalable beyond like that. It was started as a sub-project for Hadoop, and then it was created to address like bunch of issues with HDFS. So just a quick recap of HDFS architecture. You have a bunch of data nodes. You have a standby name node, active name node. Then you have a bunch of journal nodes for HA purpose. And client issues all the metadata operations on the active name node. The writes to the actual data blocks, client can do it directly with the data nodes. And it's a pipeline replication. Any data block that you write is three-way replicated. Any metadata update you make, it's returned to the quorum number of journal nodes. That is how it supports HA. A quick recap. So the problem with the HDFS or building any data lake on top of HDFS is it's bound to run into eventually the underlying problems that HDFS faces beyond a certain scale. So if you are looking at like more than 400 million files, right? Then, or if the name node if your scale grows beyond certain limits, you're gonna run into a bunch of these problems. You're gonna run into JVM heap limitations. You're gonna run into frequent GC pauses, and not just that. If your name node goes down, then it takes a long time for it to come back up again. Sometimes even hours. So, as opposed to creating your data lake on top of HDFS, if you were to do it on Ozone, all these problems, it's gonna get addressed. It's baked into Ozone architecture to be scalable beyond what HDFS could offer you. So a quick recap of HDFS Ozone architecture. So the problem that we used to see with HDFS, the bottlenecks on name node, that goes away because we separated out the namespace management and block management into two individual components. So namespace management happens on Ozone Manager. It has an inbuilt HA. By default, we run 3 different Ozone Manager nodes. It runs a rafting, all the Ozone Manager nodes are like strongly consistent with respect to any metadata that they maintain. Similarly, our block space management layer, it's called the storage container manager. Again, is strongly consistent inbuilt HA with the rafting between 3 SCM nodes. And then we have a bunch of data nodes. So, and not just that, separating out whatever name node used to handle in HDFS, we separated it out into the Ozone Manager and then the SCM component. But on top of that, we also have this abstraction of containers or super blocks. So as opposed to managing individual blocks in HDFS, we manage in terms of containers. So there itself, we get 10x scalability because individual blocks in HDFS are about 64 to 128 MB. And default container size is about 5 gig. It's configurable. You can also configure it to be 10 gig or 20 gig, and you can increase your scale factor there. And then we have a bunch of other components for monitoring in Ozone. So what's the value proposition for Ozone here? We offer incremental scalability. And again, scalability beyond what HDFS can offer. We offer denser cluster. So in Ozone, you can have up to 500 terabyte per node as of today. And then a bunch of other features that we used to have in HDFS, it's also available in Ozone. It offers eraser coding for storage efficiency. It has a snapshot feature. We provide two different types of buckets. That is for compatibility for applications. If you have applications running in HDFS, you can use FSO bucket on Ozone, and you can seamlessly migrate them to Ozone. Similarly, if your applications were running on S3 or any other object store, you can create OBS type of buckets in Ozone, and you can migrate your applications seamlessly there. And multi-tenancy is another differentiator feature for Ozone that not many object stores provide there. So what are the key value differentiators with the Ozone plus Iceberg combination? So the very first thing is you can have a faster query execution time if you are using this Ozone plus Iceberg combination. It comes from the fact that Ozone can support small files, and it can create billions of files compared to HDFS. So what Iceberg can do is it can separate out your data into smaller chunks, and your query, it can be limited to a smaller number of files as opposed to your query could be it can be constrained to only the relevant files that contains the result of particular query, as opposed to referring to some files which has huge amount of data, and then you have to do filtering by reading the individual contents of those files. It allows coarse-grained time travel, multi-table time travel. So Iceberg allows you a single table time travel, but with Ozone plus Iceberg combination, you can use Ozone snapshots, and you can do multi-table time travel. We also have integration with Ranger mapping service, so it provides better access control for Iceberg tables. We do support transparent data encryption in Ozone. And with the combination of Ozone plus Iceberg, because in Iceberg, you are not limited to physical layout of your data files. You can spread out, data files for different tables over multiple encryption zones. And, depending on your use case, you can provide better security and privacy model. Similarly, like with Ozone multi-tenancy feature, you can provide secure isolation for different Iceberg tables. So these are like bunch of these features that you will see only with Ozone plus Iceberg combination. So this one, let me pass it on to Vincent again.
All right. Thank you, Prashant. So in this section, we'll talk about some of the best practices. So Iceberg supports two modes of write operation when you're mutating data on Iceberg table. You can use a merge on read or copy on write. And the choice is basically based on your application needs. I would say it's based on the rate and ratio of data change. If your rate of change and ratio of change is small, then merge on read would be performant. So you don't have to rewrite the entire file. You are basically tracking only the records that are updated or deleted. And so it has a much higher performance on writing. And when you are reading it, then you would have to basically combine the delta file or delete file with your base file to produce correct results. Copy and write, on the other hand, is going to be efficient on read because you don't have any auxiliary files to be reconciling to produce correct results. But on the write side, it has a higher write amplification. So if you choose a copy and write, even if you update one single row on a file, you are rewriting the entire file. If the file is like 128 MB or 512 MB, then you are rewriting the whole file just for touching one record in the file, right? So it has a higher write amplification, but at the same time, it has a better read performance. So it's basically best when you're having a higher percent of change, and it really depends on the application. We have done some performance evaluation to kind of assess where the merge on read performs better, what scenarios. So we have been recommending our customers to basically look at their application usage and choose the right mode for that application. Right, some best practices. So these best practices based on our internal DPCDS performance workloads. In order to increase the number of parallelism on large manifest list files, we're recommending that you increase the number of worker threads. Also, as I mentioned, the read amplification. So repeated read of positional delete files can have a performance impact. So you wanted to kind of monitor and take care of the long tail problem. Long tail problem is when you're having the merge on read write method, every change that you are making to the table, creating these delete files or delta files. And if you're committing the transactions with a small number of records, it's going to add up. So your number of delete files is going to grow. And as you are trying to do the query processing for one base file, you may end up with hundreds of delete files because your unit of commit is very small, right? And that can have impact on your query performance. The way to address that is that basically you do a compaction. And Iceberg supports compaction through Spark procedures. So you can either automate it through our CML, Cloudera machine learning tool, which has the job scheduling, or our Cloudera data engineering has integrated with Airflow for job scheduling. So you can handle that to do the compaction. The next set of best practices basically relates to the drop table. So when you're doing a drop table, you can improve the drop table performance by setting these parameters so you can do the drop table much faster rate rather than going through synchronously deleting these files. So you can set the external table purge set to false and GC or garbage collection enabled as false. And also to minimize number of delete files. Again, this relates to the merge on read write method. When you're mutating the data, you wanted to minimize the number of delete files. As I mentioned, the number of delete files as it grows, it's going to have a performance impact because every time you are doing your query processing need not only to read the base file, you need to read all the delete files and then reconcile and skip all the deleted rows to produce correct results. To minimize the number of delete files, we recommend that you set your distribution mode to hash so you can shuffle, cluster the data, and write less number of files. As opposed to if you don't do a shuffle it, then you would basically write like a really large number of files that can impact. Starting Iceberg 1.2.0, specifically in Spark, this is the default distribution mode. Also for partial compaction can also improve performance, specifically because every write that is happening on the table need to go to the metastore to atomically swap the top level pointer. That is the contention point. Until you are committing at the metastore level, your changes is not going to be visible to anybody. So if we are writing and compacting data, you have a large compaction job that could be running for hours. and then it may conflict with another concurrent writer or delete operation. And if the conflict happens, then the whole compaction will fail, because when it tries to commit, the existing files were already modified. Right. So your compaction will basically hit a conflict and will fail, and then you have to redo the entire compaction. To avoid and reduce this conflict, we recommend you can set this partial progress, which is basically, rather than compacting a table that is 1,000 partitions with 10,000 files, you could say, I'm going to be compacting it at a partition level. So you will be a smaller unit of compaction, reduce your conflict, and reduce your failure rate as well. And you can also set this commit retry and commit number of retries setting. Again, this is relating to the write-write conflict. How do you handle the write-write conflict? How many retries should you do before you fail? And this will help you kind of handle that to increase the parallelism. That is the end of our presentation. So if there are any questions, either to me or Prashant, I can answer those questions at this time. Thank you, everyone.
I have a question regarding that. You mentioned Iceberg replication.
Yes.
Under what context is the replication necessary, and do you guys guarantee consistency, and how does that work? And for the replication, is that cross multiple Ozone clusters? I'm not too sure about the concepts there, or it's cross data centers, or it's cross regions. So still back to the question of context or replication.
Yeah, good question. And we also have our product manager, Shiv, here, who owns the replication product roadmap also. So he can chime in as well. I'll start with that, and then Shiv, please chime in.
You want replication, you need or data.
Other question.
Okay.
Because he didn't mention that in the slide.
Yeah, there's two different things. Yeah. Okay. Yeah. Got it.
So I will cover the Iceberg replication side of it. Right. So Iceberg replication, the one that we GA'd in our private cloud base or on premises support is right now it is only supporting HDFS to HDFS, where your storage is on the HDFS. We will replicate from a HDFS cluster to an HDFS cluster. And it can, primary purpose is for disaster recovery. And also, if you wanted to offload your read workloads to the target side, so you can get more capacity on your active side, that is also another use case where we have seen customers have been asking for that. We do have a roadmap to support Ozone and also cloud-to-cloud replication as well. Because as you know, there has been a number of incidents where even our biggest cloud storage provider has been hitting with failure rates, right? So our customers who are really mission critical customers do not want to rely on cloud storage providers guarantee of 5 nines. They need to make sure that they can guarantee they can handle their business continuity, and that's why they are asking for this replication even in a public cloud environment.
Yeah, so just to add on to that, if your Iceberg tables are on top of Ozone, you can also take advantage of Ozone replication for DR purpose, and it would just work.
Okay, it's for DR, not for all active, so that like there's no consistency, like very short SLA needed on the other side to access the data.
It is not right now in the roadmap, but basically we are still talking to customers. If there is a higher demand, we will actually look at that. But are you specifically asking for active-active?
Yes.
Yes. The active-active, yes, it has its own usage scenarios and requirements, but it's also challenging because you need to handle with the conflict resolution when you have two sides of modifying, mutating the data, right? So it has its own challenges, but we haven't seen really a lot of customers asking for that right now. The more important use cases are disaster recovery.
Okay.
Right.
Cool. Thank you.
Yeah, very great questions. Yeah, thank you.
So that is also one of the key differentiators that you get with the Ozone plus Iceberg combination. If you were using Iceberg on any other storage system like HDFS or S3 or anything else, so as Vincent mentioned that there is a separate Iceberg replication available on HDFS, but they have to do it for every different type of storage engine. It kind of becomes a challenge, right? And that kind of support may come over time. But if you use Ozone-like storage system, you can just leverage the capability that it provides.
A question for Uber. Have you looked at Iceberg? Have you considered Iceberg? I'm really curious that have you actually looked at it, considered? And
we are, of course, on Hoodie, right? So, but also we are looking into Iceberg, see like do some of this kind of competitive analysis.
Okay.
And see like what potentially can also be borrowed and even like kind of like push also to the Hoodie, etc. Right? So
okay. Yeah. So any particular reasoning why you chose Hoodie versus Iceberg?
I think Hoodie was originally incubated from Uber.
Oh, okay. Okay, right.
Yeah.
There are three open table format out there, right? As you know, Hoodie, Iceberg, and Delta, right? Each has their own strengths and capabilities and differentiators. Iceberg in particular has this partition evolution, which not the other two has. Hoodie has its own strengths and like it has supports indexes and so on, right? So that's why I was curious. So yeah, thank you. That's not. Do we have any questions on the Zoom? It's asking about something that I don't.
Is asking, I would like to rely from Iceberg with OFS, but it doesn't seem to be possible right now. Is there any support like GCS file IO, no, GCS like Ozone equal to file? Okay, I get that question. Yeah, so we support this. So if you want to use the Iceberg plus Ozone combination, you can use the OFS URL as well as you can use the S3A URL. We have published a blog on this, like how you can achieve this. We can send you a link and you can refer to that. There's another question with 10 billion scalability with small scalability, will small files no longer be a performance problem in Iceberg and Ozone? I believe so. That was our point of presentation. No questions on Zoom. Any more questions on Zoom? Yep. Yeah.
Yeah. Thanks everyone here and in the Zoom. Thanks for the speakers, really great presentations, namely Swami, Aswin, and Prashant, and Vincent. And from Uber, they gave a great presentation on HDFS, Jing and Fengnan. Thank you so much. And the many of folks who made it to in person. It was a great to meet you all. Yeah, I think we would continue to have this kind of events in the future, and we'll stay tuned for the next event. Yeah. Yeah, thanks everyone. I think we'll end the talk for the day. shortly, I think we will post the recording. We recorded all the sessions. We pretty much, I think we will post in the same Meetup link. So whoever interested, you can come back to the Meetup link and look at it. And you can also reach us any of the Apache channels like Slack or mailing list, in any channel. So we would be happy to answer your questions. Thank you.